Welcome to the first in a series of short videos which aim to demystify FloEFD, a CFD tool from Mentor Graphics. FloEFD for Creo is a unique engineering tool which allows you to increase productivity and quality of your designs by front-loading CFD. Front-loading CFD refers to the practice of moving CFD simulation early into the design process, enabling you to examine and evaluate multiple design options, ultimately resulting in an optimized product performance and reliability. FloEFD technology can reduce simulation time by as much as 75% compared to traditional CFD tools. Let's see how. One of the headline features of FloEFD for Creo is the fact that it's a Creo Embedded CFD tool. On the screen we have PTC Creo Parametric 3.0, and FloEFD plugs into the software with its own ribbon toolbar and FloEFD feature tree. Being Creo Embedded has several advantages, such as being able to determine the blue fluid volume quickly and natively in Creo. Boundary conditions are also applied directly onto the Creo geometry by selecting faces in the view window. In this instance, we have an inlet velocity and 4 outlet pressure conditions. Post-processing is performed in the Creo visualizer also. For example, cut plots can be created and overlaid over the geometry and animated so they move through the assembly. This cut plot shows the velocity distribution slicing through the model. Flow trajectories show how the fluid looks dynamically, and by zooming into the throttle body, this shows how the flow is being deflected and guided down the intake runners. Being Creo Embedded means that we can make parametric changes to the model very easily. Looking at the velocity beforehand, we can see a maximum velocity around 13.7 meters per second. Now we change the Creo angle constraint of the throttle body from 40 to 30 degrees and run again. The velocity has increased to 20 meters per second due to the more restrictive throttle position. This will have effects downstream with respect to the pressure drop and runner flow rate distributions. Being Creo Embedded makes variant analysis and optimization very quick and easy to perform. The second key feature is the ability to handle complex arbitrary volume solids using immersed boundary Cartesian meshing. Here we have a motorcycle headlight unit which we wish to mesh. FloEFD handles this complex shape very quickly using automatic or manual mesh settings. FloEFD uses the Cartesian meshing schema, which can be seen here with increasing mesh density levels closer to the volume. FloEFD also has the ability to handle multiple control volumes within a single cell. This cell has 3 control volumes. The mesh can be visualized further by moving the plane to a desired location. Mesh refinement levels can be visualized, and in this example, we have a range between 0 and 3, 0 being the base mesh. Multi-control volume cells can exist at any mesh level. A 3D representation of the mesh can be projected onto the geometry to check for mesh quality and refinement levels. FloEFD is very tolerant of dirty geometry such as overlapping components and handles complex shapes very easily due to the fact that a fine boundary layer mesh does not need to be generated. The third key technology is how FloEFD handles the boundary layer which forms on the surface of a solid. This example is using a heatsink in a wind tunnel to determine thermal resistance and pressure drop characteristics. Looking at the mesh shows the Cartesian nature again with finer grid levels around the heatsink fins. Multi-control volume cells exist at the walls, which is where the proprietary wall function is applied. This allows for coarse meshing at the walls whilst retaining the correct flow and heat transfer characteristics. Looking at the velocity, we can see the boundary layer at the walls, and the boundary layer grows as the flow moves from left to right. We can see the same boundary layer growth if we look at the walls of the wind tunnel also. To validate this approach, let's look at the pressure distribution at 4 meters per second airflow. The CFD predicts a 3.9 millimeters of water pressure drop total. The datasheet for this heatsink has a pressure drop of between 3.8 and 3.9 millimeters of water. The benefit is that we do not require a dense wall mesh and still get accurate results, negating the need to be a meshing expert. The final key feature is the turbulence modeling in FloEFD. In this example, we're going to be looking at an external aerodynamics application of a subsonic aircraft. By going into the general settings, we can see the options we have available for turbulence. FloEFD uses a two-equation RANS turbulence model, which can be defined either by intensity and length or energy and dissipation. Looking at the mesh from the side, solution adaptive meshing has been enabled and is evident by looking at the increased mesh density in areas of high flow gradient. The mesh around the wing is also refined, especially around the leading and trailing edges. Looking at the velocity, we can see the high velocity along the top surface and lower along the bottom, as we would expect, and this gives us lift. Turbulence parameters can be visualized. Here we have the turbulent energy, which can be seen along the top surface and trailing edge. Turbulence dissipation can also be seen the most along the leading, top face and trailing edge where the two streams combine. Turbulence intensity shows where the most turbulent area in the model is, and this is seen at the trailing edge and the downstream wake. Flow around the aircraft shows the velocity vectors and in particular the wingtip vortices. These can be isolated and colored by turbulent energy, which shows the chaotic mixing nature of the flow at the wingtips. In conclusion, FloEFD has several unique proprietary features which make CFD analysis faster and more accessible to design engineers. The main hurdle traditional CFD engineers face is generating a grid-independent mesh which converges accurately in an acceptable time. FloEFD removes this specialization and makes CFD more accessible to users. Complex geometry handling, without having to worry about boundary layer meshing, whilst being MCAD embedded, makes FloEFD a front-loading CFD tool for engineers and not analysis experts. Flow and thermal optimization earlier in the design cycle means less physical prototypes, more reliable products, and faster time to market.